Hello everyone, how's it going? My name is Dan the Tutor, on a quest to become the world's greatest tutor. In today's video, we're going to talk about the continuity equation for fluids. So here's what we're looking at. We have a big section of pipe leading into a much smaller section of pipe. And so basically what we notice, if we do this in real life, that the velocity here is very small. In other words, the fluid is moving very slowly. And then when we get into this tight region right here, the fluid starts moving very fast. V, the velocity, is a very large number. Which I'll admit, for me, when I first learned this in college, I was very confused by this fact. Because if you use the analogy of like cars on a highway, if I have a 3-lane highway, aren't the cars going to be going faster than a 1-lane road? You know what I mean? But as my professor explained it to me, no, that's not how it works. And we'll just leave it at that. So I don't have a good analogy for this, but I do have a very good equation, which again is the continuity equation, which is to say that Q1 equals Q2. What the heck is Q? That's the flow rate, which is going to have the units meters cubed per second. Or you could also do liters per second or liters per minute. In other words, it's a volume divided by some unit time. That's what flow rate is, a volume over time. But Q1 equals Q2 is not very helpful on its own. We need to know that Q is equal to A times V, where A is the cross-sectional area. So for instance, if I were to take a slice out of this tube right here and find the area of that slice, that's what the cross-sectional area would be. Usually, if it's a circle or a cylinder, it's going to be pi r squared. Sometimes it's a rectangle, length times width or length times height. And then V is not volume, it is velocity. And we know that because it's lowercase v, uppercase V is volume. And so basically, rewriting Q1 equals Q2, we get A1 V1 equals A2 V2. And basically what you need to know is, because it's multiplication, A1 times V1, these two things are going to be inversely proportional. In other words, if I have a big area, I'm going to have a small velocity. And if I have a small area, I'm going to have a large velocity. And basically, we use this equation whenever we have fluids flowing from a big section of tubes to a small section, or vice versa. And it's also used a lot in Bernoulli's principle, which I'll be covering in the next video. So now let's just do a couple practice problems with this, and we'll be on our way. For this first one, it's a very similar picture to what I just drew. I have a big section of tube flowing into a little section of tube. The radius of the big section is going to be 15 centimeters, and it's going to be flowing into a size a third as big to 5 centimeters. And if the velocity at this end of the tube is 2 meters per second, I want to know the velocity at this end. So this isn't bad at all. We're literally just going to use the formula I just said. A1 V1 equals A2 V2. In this case, the cross-sectional slices are circles because we're having a cylindrical section of pipe. So in other words, it's pi r1 squared times velocity 1 equals pi radius 2 squared times velocity 2. Now we notice pi cancels, which is nice. R1 was 15 centimeters. I guess I should convert that to meters, right? So that's going to be 0.15 meters. And then we're going to square that. Times V1, which is 2 meters per second, equals R2, which was 5 centimeters, which is going to be 0.05 meters squared. And then we're just solving for V2. Now all I need to do here is divide both sides by 0.05 squared. And that's going to be my new velocity. And that means V2 is going to be, final answer, 18 meters per second, which is significantly faster. And by the way, maybe a real-world application that you can actually picture is that when you have a garden hose, right? And you cover part of the garden hose with your thumb, doesn't it make the water like spray out like crazy at a crazy high speed? That's exactly what's going on. It's the continuity flow equation in action. One more thing about this problem before we go to the next one. If I just use generic variables, like here's what I mean. This was pi r squared V1 equals pi 1/3 r squared V2. Sometimes you have generic variables like this, right? And I'm saying 1/3 the radius because that's what it was. 15 divided by 3 was the 5 centimeter radius. So anyways, how would I solve this one with just generic variables? I would first square both things, so it's now 1/9 r squared v2 equals pi r squared v1. And now I can cancel nearly everything. Pi and r squared both cancel. And all I'm left with is v1 equals 1/9 v2. So if I want to solve for v2, just multiply both sides by 9. And so that means no matter what the actual numbers were, the answer was always going to be 9 times v1, which of course makes sense because we got 18 meters per second, which is equal to 9 times 2 meters per second was the numbers from that first problem we did. So just another way of thinking about it. Sometimes they give you these comparison problems, and I need to make sure we're ready for it, right? And now I got one more for us today. This one I'm going to have to type out because it's pretty long. So here's a famous problem that I've seen before. The ascending aorta has a diameter of 2 centimeters. Blood flows through this aorta with a speed of 0.3 meters per second. It then flows through the capillaries with a velocity of 0.001 meters per second. If each capillary has a diameter of 5 micrometers, how many capillaries are there? So this one's interesting. If I were to draw a picture, basically what's going on is we have some tube in our body, the aorta, that's splitting off into like a million of these capillaries. Now each individual capillary is very small, 0.5 micrometers in diameter. However, since there's so many of them, if you were to add up all these areas together, it's actually going to be larger than the aorta, and by a lot too. But the good news is we are using the same equation, A1V1 for the aorta equals A2V2 for the capillaries. Area 1, okay, first of all, I gave us not only in centimeters, but diameter, right? So radius 1 is going to be 0.01 meters. I divide it by 100 to get to meters, and I divide it by 2 to get to, well, radius. And again, we're assuming these are cylindrical pipes, essentially. So it is going to be pi r squared for the area equation here. So in other words, area 1, pi times 0.01 squared times velocity 1, which we said was 0.3. So 0.3 equals, now I have to find area 2. So the diameter is 5 micrometers. Remember, that's 5 times 10 to the minus 6 meters. And then dividing that by 2 to get to radius. Radius 2 is going to be 2.5 times 10 to the minus 6th. And I'm going to plug that in for A2. Pi times 2.5 times 10 to the minus 6 squared times the velocity, which we do know, 0.001. And then I have a question for you. Number 1, what am I solving for? I don't have any variables, number 1. Number 2, if I were to plug in both of these things in a calculator, they're not even equal to each other. So what mistake did I make here? Well, I'll tell you. I made a mistake with the area of 2. This is the area for 1 capillary. I don't know how many capillaries I have. Maybe I'll call it n. So I need to multiply this area by n and then times the velocity 0.001. And now I'm solving for n and I know what to do. So first, pi cancels, which is nice. And then if I want to solve for n, it just means I'm dividing both sides by 2.5 times 10 to the minus 6 squared times 0.001. That's in the denominator. I recommend doing this in a couple steps in your calculator, especially if you're not super strong with your calculator and you're afraid you're going to make a mistake. And we'll get, holy crap, this is a ginormous number, 48,000,000,000, which is 4.8 billion capillaries. I have no idea if this is accurate or not, but it doesn't matter. And if you want that in scientific notation, that's just 4.8 times 10 to the 9th, which looks much better. But that's how we solve this problem, using the continuity flow equation. And you're always going to use this equation whenever you have a changing radius in your pipe and the fluids flowing through it. Well, that's going to do it for this video. Thank you all for watching. Hope you have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.